All right, welcome to this unit, more experimental research. We're going to talk about weak and strong designs and a couple additional issues with experimental designs. So just to review, we've talked about experiments. Experiments are situations where we're creating a highly controlled situation where we can randomly assign people to conditions and we can manipulate a variable so that we can determine cause and effect. Ideally, we're looking to see if our manipulated independent variable has a causal effect on some dependent variable. We can do this in the field like we talked about last time. We can do this in the laboratory, a room on a university campus. We can also do this via the internet. Um, so there are ways to randomly assign people to conditions using internet protocols like Qualtrics. You can also do this within other forms of internet experiments, like the implicit association task. If you're not certain what that is, Google implicit association. And there's a variety of ways we can do that in experiments. But the focus today is going to be on different kinds of research designs and the strengths and weaknesses of those. And again, there's different ways we can manipulate the independent variable. So treatment versus control, this is sort of like presence or absence. In our caffeine example, where we were asking the question, does caffeine improve intelligence? When we create a single pot of decaf coffee and then half of the participants receive caffeine, the other half don't, this is a presence or absent type of manipulation. We could moderate that. Perhaps we think that more caffeine is going to produce a stronger effect. And so we might have a low dose, a medium dose, and a high dose. That would be varying the amount. You can also pit two different forms of the independent variable against each other. So perhaps you have two different early intervention reading programs, and you want to see which one is more effective. You could have, strategy 1 versus strategy 2. I would say for those kinds of studies, though, you do always want to have a control group for maturation issues as well as regression of the mean issues, which we talked about last time. Now, ideally, we want to have control in our experimental study. This can be through random assignment, right? So randomly distributing extraneous variables that might influence our dependent variable across multiple conditions of our independent variable. Or this could be through study design. So making sure that our two conditions are identical as possible except for that independent variable. Now, there's different ways that we can make sure our two groups are identical. So our levels of our independent variable are identical. We talked about randomly assigning people to conditions, but there's a couple other ways that we can do this. So matching is a good way. This is often done in experimental research. Oftentimes we can't, or most of the time, when we're doing educational research, we can't randomly assign people to students to schools, right? Students are in the schools that they're in. And if we have some program and we'd like to implement the program at one school and then compare that to a control school that doesn't get that program, one way we can make sure those groups are relatively equal is by matching the students. So if I have, a female fourth grader who identifies as Hispanic and who falls into this tax bracket, and then I make sure that at my control school, I also include in my study a student who matches that demographic profile. We can match individuals on a variety of things. So we could ask, questionnaire survey items and match participants that way. This is a little bit more complicated and time-consuming, but when you can't randomly assign, matching individuals and groups is a good way to get your experimental group and your control group together. And there's a variety of ways that we can do that. We can hold extraneous variables constant, so we can only look at, one subset of the sample. So, we can only look at women, and that controls for gender. The other way we can do this is by measuring our extraneous variables and then using them as part of our statistical analysis. So ANCOVA, analysis of covariance, is a statistical tool that we use when we want to ask the question, does a categorical independent variable have some effect on a continuous dependent variable? And we would like to control for a variety of continuous independent variables. So for example, let's say you're interested in the effects of a reading intervention program on elementary school age children. You're working within a single school, and this allows you to randomly assign students from a pool of at-risk students. One group gets the early intervention reading program. The other is waitlist control, which means that at the conclusion of the experiment, they will also get the program. So we've randomly assigned these students, but we also think that there might be other variables that might influence how well they read beyond this treatment. So we measure, we implement the treatment and we measure their reading proficiency following the treatment, but perhaps we also measure, their parents' level of income. We measure ethnicity. We measure the amount of time that their parents spend reading to them. We, measure whether or not they attended a high-quality preschool, right? So we have all of these other variables, and when we throw this into our model, our main independent variable is the treatment program, and our main dependent variable is their reading performance. But what we do with these covariates, these additional variables, is we enter them into the model, and what they do is they remove variability in the dependent variable that is associated with those covariates, right? In other words, if you imagine that the reading performance represents 100% of the variability in reading performance, and let's say 10% of that variability in reading performance is related to whether or not you went to a high-quality preschool, unrelated to the intervention. When we throw those covariates in, that covariate removes that 10% of variability so that we're only looking at the variability in the dependent variable that could be related to the independent variable. I hope that wasn't confusing. If you have questions about that, certainly email me. Now, we talk about weak experimental designs. They're weak because they don't control for extraneous variables. They don't have random assignment. You might have selection bias. So, for example, maybe we go into the classroom and we tell the students, hey, maybe they're 8th graders, let's say. We tell them, we've got this reading intervention program, and you can choose to participate or not. And the students who choose to participate go in the experimental group, and the students who choose not to participate go in the control group. And lo and behold, we find that the students in the treatment group had a greater reading performance following the treatment. Right? This represents a selection bias because the participants self-selected into the experimental or control condition, which suggests that there might be a confound of motivation. Perhaps the students who self-selected into the experimental group have a higher level of motivation than the students who don't, right? So this is an example of a weak design when we have these sort of selection biases. Strong experimental designs are going to control for most of our extraneous and confounding variables. There's a couple different kinds of designs. We've talked about these. So the one group post-test only design is when we have a single group exposed to an experimental condition, and then we measure their dependent variable. So this would be, we have a reading intervention program, we go to a classroom, everyone in the class gets the reading intervention program, and then we measure their reading performance afterwards, right? And this is a super weak design. We basically can't learn anything from this design because we have no comparison group, right? We didn't pre-test them, so we can't compare to their performance before, and we don't have a group that didn't get the reading intervention that we can compare them to. So this is almost not even a research design. It's a super weak design. There's a couple other ways we can make this stronger. So one way is with a between groups post-test only design. In this case, we're going to randomly assign participants, so that's key, to 2 or more groups. These groups we can consider to be levels of the independent variable. And then we can measure them on some dependent variable. So for example, we could randomly assign undergraduates to think about a time when they were socially included or socially excluded. Social ostracism, social inclusion is huge in the field of psychology right now. And one might hypothesize that remembering a time when people excluded you might make you feel bad, or might make you feel sad, might make you feel a little down, whereas remembering a time when you were included might make you feel good. And some researchers were asking this question: would social exclusion or inclusion have an effect on people's perception of the temperature of the room? And this is real research, by the way. And the hypothesis here is that we associate negative things with coldness, and we associate positive things with warmth. Like, we like warm people, we don't like cold people. And so the hypothesis was that people who think about being socially excluded might actually perceive the temperature of the room that they are sitting in as colder compared to the people who recall the time when they were included. And this is what these researchers found. I have a link there to the study if you're interested. This is a post-test between groups because we've got 2 groups, and it's post-test only because we did not pre-test them. This is a perfectly legitimate design. We would consider the between groups post-test only a strong design. Now, we could change this to be a pre-post design. This is a little bit stronger because we have more information and there's more comparisons that we can make. So we could, theoretically, randomly assign these same participants to one of 2 groups. We'll have them rate the temperature of the room, then present our experimental manipulation, remembering social inclusion or exclusion, and then have them rate the temperature of the room again. Now, what's useful about this between groups pre-post design is that it allows us to make multiple comparisons. So we can compare the group averages of temperature of the room following the manipulation. So we can ask the question, are the people who recalled social exclusion rating the room as colder compared to the people who recalled social inclusion? We can also compare them beforehand to verify that the random assignment worked, right? That they're equally rating the temperature of the room. And we can also ask within subjects questions, within participants questions. Did individuals change from time 1 to time 2? Okay. So between groups pre-post is a better design, stronger design, because it allows us to ask a lot more questions of our data. Now here's another example of this. So we can look at this change over time when we have these between groups pre-post design. So a couple researchers were interested in the perseverance of children on tasks and the way that they are praised for those tasks. So particularly they're interested in what we call person praise versus process praise. Person praise is when children are praised for their performance, and that performance is tied to who they are. So students are brought into the lab, they're given a series of puzzles to complete, and for the person praise group, after they complete the first set of puzzles at time 1, the researcher comes in and says, "Oh, look at you, you did such a good job completing these puzzles. You must be really smart." Right? So when the child asks, why did I do well in the puzzles? I did well because I am smart. That's something about me. Process praise, on the other hand, is about, as it sounds, the process. Right? So the researcher comes in for this group and says, "Oh, you did really well on these easy puzzles." Well, they don't know that they're easy, but they're easy. "You did really well on these puzzles. The reason why you did this, you worked so hard on this puzzle. Good job. You worked really hard." right? So for these children in this group, when they ask themselves, why did I do well on the puzzles, the answer is because I worked hard. Okay. Then, what they do, and this is kind of mean, sometimes psychologists were mean, they induced failure between trial 1 and trial 2. So the participants, the children come in, they complete a series of puzzles. Some of them are told they worked hard, that's process. Some of them are told the reason why they did well is because they're smart, that's person. And then they induce failure. They give them a puzzle that is impossible to complete. And by puzzle, think like Sudoku for kids kind of thing. Okay? So it's impossible for them to complete. So they let them sort of struggle with this impossible puzzle. And then they say, you know what, that was a really hard puzzle. Let me give you some other ones. Okay? And they give them a second set of easy puzzles. And then they measure their performance on the second set of easy puzzles. So hopefully you're all with me. If not, rewind. Okay. What happened then? Well, for the group that was in the process praise condition, they actually improved their performance following failure, right? So the number of puzzles they completed at time 1 went up dramatically at time 2. But the group in the person praise actually did worse the second time following failure. Okay. Now, this is what we call an interaction. This would be an ordinal interaction, a spreading interaction. We'll talk about this a little bit later on in this lecture. But what happened here? Why did this happen? Well, what happens is, for children, when they are person praised, when they're told that their performance is about who they are, who a person is what we call a fixed attribute. There's really nothing you can do, like either you're smart or you're not. And for kids who are process praised, the process is not about who you are, it's about what you do, right? So this is not a fixed attribute, it's something you can control, you can work on. So what happened in this study is that when the children were experienced failure, the conclusions that the two groups came to were different, right? So when the children experienced failure for the person praised group, when they asked themselves, why did I do well in the puzzles before? Well, it's because I was smart. Why did I fail at this puzzle now? It must be because I'm not smart. And that led them to work less diligently on the puzzles at time 2. On the other hand, the participants, the students in the worked hard condition, when they asked themselves, why did I do well? It's because I worked hard. Why did I fail? Well, I didn't work hard enough. And so they ended up working even harder on the second trial. So this is a really good example of this between groups pre-post design, right? We can see how these students are changing over time in these two experimental conditions as a result of our experimental manipulation. Typically, when I give this portion of the lecture in face-to-face class, students have lots of questions. So if you're interested in more information, shoot me an email and I can give you more information about this study. So we touched about this idea of a within groups design. So in the pre-post design, that's technically a within groups design. It's between subjects or between groups because we're randomly assigning the conditions. But we don't always have to do that, right? We might measure the same participant more than once in the same variable. And when we do this, we're interested in the difference between these two variables. So standard pre-post tests are examples of paired data. So if we are trying to help someone lose weight, maybe we measure their weight at time 1, and then we put them on a television show where they're on a strict diet and people yell at them, and then we measure their weight again at time 2. This is an example within subject design. We're asking the question, does the intervention lead to a change within individuals from time 1 to time 2? And the question we're asking here in this example is there significant weight loss? So this sort of looks like this. There's some pre-study measurement, there's some kind of intervention, and there's some post-study measurement. Another example of this comes from the television science show Mythbusters. So does swearing increase pain tolerance? So in this study, they induced pain with ice water. If you've ever put your hand in the bottom of a cooler during a barbecue in the summer, you will have undoubtedly noticed that you go from 0 to instant pain pretty quickly. And then what they did in this example on this show was they had the host of the show either yell random words or yell swear words. And the question they're asking was, do the swear words increase the amount of time that participants can tolerate the ice water? So if you're interested, you can pause me real quick and click on this link, and it'll take you to a video clip of the host of the show doing this. Now, one thing that is cool about repeated measures designs is that each participant serves as their own control. So what you can do is you can control for variability across participants. So one thing that might influence how long a person can keep their hand in that bucket of ice water is baseline pain tolerance, right? Some people might have higher pain tolerance than others. But we're not interested in the difference between your pain tolerance and someone else's. We're interested in how much longer you can keep your particular hand in the bucket of ice water when you're swearing compared to when you're yelling random words. Right? So you effectively serve as your own control group. This is super efficient. So in terms of statistical power, you need less participants when you have within groups design because you have more power. And you get pretty good efficiency, right? So we're removing variability that's unrelated to or that we're not interested in. So think of things like baseline pain tolerance, and so then we're only looking at differences across these levels of independent variable. Now, there are some disadvantages to repeated measures designs. One, experiencing the pre-test can influence the post-test, and this could be order effects. So practice, you might just get better over time. So if you watch that Mythbusters clip or if you saw the entire show, one thing you might have noticed is that when the hosts of the show put their hand in the bucket of ice water, all of them put their hand in the bucket of ice water and yelled random words first, and then they yell swear words second. And so this is problematic because maybe the swear words swearing is what's helping them to keep their hand in that bucket of ice water longer, or it could be a practice effect. They're just getting desensitized to the ice water. They're getting used to the task. They're getting better at it. So order effects are a huge issue in repeated measures designs. Also, carryover effects are problematic. So changes caused by participation in earlier treatment condition. You might, let's say, observe some changes in your dependent variable following your independent variable, but those changes only exist because of some aspect of the participation. So, for example, a researcher and I were interested in whether the kind of language used to describe the gay rights movement had an effect on African Americans' support for the gay rights movement. Specifically, what we were thinking was that perhaps African Americans might be upset by the fact that the gay rights movement is using language, co-opting language of the Black civil rights movement. And what we found in this study was that we had some carryover effect. We used a survey methodology and we asked participants to identify to indicate how much they identified with the civil rights movement. How important is this to your sense of who you are? These kinds of questions. And then we asked them how upset they were about the gay rights movement co-opting the language of the civil rights movement. And what we found was that when we asked the questions in that particular order, the people who identified with the movement were more upset about the gay rights movement co-opting that language compared to the people who were low identified with the civil rights movement. But in a subsequent version of that study, we were unable to replicate that result when we changed the order of the questions. So it's a long way around of saying that answering the questions about their civil rights identity is what led to those changes in the subsequent questions. And if we change those order effects go away. So this is, again, a particular sequence leads to a particular effect. Now, one way we can get around this is through counterbalancing, changing the order of conditions so that we can cancel out sequence and order effects. So if you think about the Mythbusters example, they had them yell swear words and yell random words. Time 1, they always did random words, and time 2, they always did swear words. And so this is problematic because you can't rule out order as a potential confound, right? Because this is systematically varying. So what we do is we counterbalance. Half of the people get this order, the other half swear first, and then they get the random words at time 2. Now, if the hypothesis is true, if the hypothesis is supported that swearing improves pain tolerance, then we should see higher amount of time, higher pain tolerance in both the swearing conditions compared to the random conditions, no matter what the order is. But if what we're seeing here is an order effect, then we would see a higher pain tolerance at time 2, regardless of what words they're using. Okay, and so counterbalancing is really cool. It's a good way to cancel out these order effects. All right, the last thing we're going to talk about today is factorial designs. So a lot of times, up until this point, we've sort of talked about a single independent variable influencing a single dependent variable. But a lot of things in life are overdetermined, right? Your behavior in a particular moment or a student's behavior in a classroom is not just about one variable or another. There are thousands of variables that influence that behavior in a particular moment. And so oftentimes when we do research, we're interested in looking at more than one independent variable at a time. And when we do that, we end up having a factorial design. So if you think back to the effects of caffeine example that we used, does caffeine improve intelligence? We might also be interested in the amount of sleep that a person got and the effect of sleep on intelligence. So I'm sure as you've had experience, if you get terrible sleep or not enough sleep, you feel a little groggy in the morning and you have a hard time sort of thinking. So it could be that sleep is another independent variable that affects how well students would perform on an intelligence test. So what we would do then for this example is, let's say we do a sleep study, and people actually do this, where participants come into our lab and we have a room set up for them to sleep in, and we randomly assign them to one of two conditions. Either we're going to let them sleep the whole night, and 8 hours later we're going to wake them up, or we're going to wake them up after 4 hours. Okay. Then, once we've woken them up, either after 8 or 4 hours, we're going to randomly assign them to either get a cup of decaf coffee with 100 milligrams of caffeine or no caffeine, and then they're all going to take the intelligence test, the dependent measure. What this means is that now a participant in this study can be randomly assigned to one of 4 possible conditions. So we have 2 levels of our independent variable of caffeine, either 100 milligrams or none, and we have 2 levels of our independent variable of sleep. Either we're going to let them sleep for 8 or 4 hours. And this is what we call a 2x2 factorial design, because we have condition 1, or variable 1 has 2 levels, and variable 2 has 2 levels. And 2 times 2 is 4, which means there are 4 possible conditions that our participants could end up in, right? So when you walk in the door as a participant, you might be in the 8-hour group that wakes up and drinks no caffeine, or you might be in the 8-hour group that wakes up and drinks 100 milligrams. Now, we're not limited by the levels of our independent variable, so maybe we're interested in looking at the dosage of the caffeine. So we add a third group, a 200 milligram group, to see if more caffeine leads to a greater improvement. We would call this a 3x2 factorial design, because there are 3 levels of three levels within independent variable 1, 2 levels within independent variable 2, and now there are 6 possible conditions that a participant could get randomly assigned into. You can keep adding independent variables, right? So technically there is no limit to the number of independent variables you can add. Practically speaking, though, 3 or 4 is pretty much the ceiling, just because the analysis and the interpretation gets really dicey after 4 levels. So you can imagine maybe we are also interested in looking at gender. So we'd be comparing males and females in this same study. So that would be a 3 by 2 by 2 factorial design, because we added that third independent variable of gender. So we would end up with 12 possible conditions, right? Males with all 6 of these, and then another table just like this with females with all 6 of these. So as you can imagine, this can get very complicated very quickly. For today, we're going to stick with the 2 by 2 because it's simple to think about. Now, when we have factorial designs, this allows us to test hypotheses about both independent variables in the same study. And we can look at the independent variables separately. And when we do that, we call those main effects. So does caffeine increase intelligence controlling for sleep? Does sleep increase intelligence controlling for caffeine? This is a main effect. Now, when I say controlling for, what I mean is, if we think back to this table here, when we randomly assign people to the 4-hour, 8-hour group, and we want to just see if there's a difference on sleep, the people in the 4-hour group, some of them got 100 milligrams, some of them got none. People in the 8-hour group, some of them got 100 milligrams, some of them got none. So because of that, we're controlling for caffeine, right? Because half of the people in the group got some, half of them didn't. That cancels it out, so we're controlling for caffeine. Now, main effects are just about independent variables independently. How does this independent variable controlling for the other one affect the dependent variable? But we might also be interested in combinations of variables. So perhaps sleep moderates the effectiveness of caffeine on intelligence. So maybe when people have 8 hours of sleep, they're going to score the highest on intelligence compared to 4 when they get caffeine. Okay, this is what we call an interaction effect, an interaction between 2 or more independent variables. Interactions are always what we talk about as moderators, right? They turn up or turn down the effects of the independent variable on the dependent variable. So, for example, perhaps we think that caffeine improves intelligence, especially when someone's gotten a full night's sleep. What this suggests is that sleep is moderating the effect of caffeine on intelligence. Sleep is turning up the effectiveness of caffeine on intelligence. So far we've talked about hypotheses about main effects, right? Is the caffeine group going to score higher compared to no caffeine group? Are the people who wrote about social inclusion going to rate the room as warmer compared to the people who wrote about social exclusion? These are all main effect questions. Interaction hypotheses usually involve this moderating or qualifying language. So if you're making a hypothesis where you're saying there's an effect of X on Y, especially when this happens, or only when this happens. This kind of language indicates an interaction hypothesis, that one independent variable is moderating the effectiveness of the other independent variable on the dependent variable. So, if we ended up doing this study, and we brought participants to our lab, half of them slept for 8 hours, half of them slept for 4, half of them got 100 milligrams, half of them got none, and we have their 4 conditions here. And we get their average intelligence score for each group. If there was a main effect of caffeine and no effect of sleep, what we would expect to see is that regardless of how much sleep you got, you're going to score higher on the test when you got 100 milligrams compared to none. Okay. And what this would look like is that within the caffeine groups, there's no significant difference between the sleep conditions. So this might look something like this. This is what we would call a main effect of caffeine. So the people who got the caffeine are scoring higher compared to the people who got nothing, regardless of how much sleep they got. Main effect of caffeine. Now, it could happen the other way. Maybe caffeine has no effect and it's all about sleep. So maybe we would get a main effect of sleep. Now, in this case, within the sleep condition, there's really no effect of caffeine. So whether you got 100 or none in the 4-hour group, it doesn't really matter. What matters is the amount of sleep that you got. And this would be what a main effect of sleep looks like. So here you can see everyone did really well when they got 8 hours of sleep, regardless of what condition they're in. So this is a main effect of sleep. Okay. Now, what if we ended up with an interaction? Okay, what would an interaction look like? And we'll talk about a couple different kinds of interactions. So what if the caffeine group scores significantly higher in intelligence, especially when they've got 8 hours of sleep, right? So sleep turns up the effects of caffeine on this intelligence. So now we've got these means here, and we end up with something that looks like this. So the people in the 100 milligram group who got 8 hours of sleep scored significantly higher than the people in the 100 milligram group who only got 4 hours of sleep. This is what we would call an interaction effect. Your book, and you'll see this in a little bit, is going to call this an ordinal interaction effect, or a spreading interaction. We might also ask the question, is there a main effect of caffeine? And the answer is probably, right? So if we collapse these two conditions together, the average of this and the average of these two, there's probably also a main effect of caffeine. So you can have main effects that are significant and interaction effects that are significant as well in your analysis. Now, we can also, so I've been representing these as bars. We can also represent interaction effects as lines. So this is the same effect that we were just looking at on this slide, now represented as lines. Your book is going to talk about this as an ordinal interaction. We can talk about this as a spreading interaction. The key to these ordinal interactions is that the lines are not parallel. So if we looked at this main effect here, and if I were to change this, to a line graph, which I'm going to do now, right? Notice that the lines are parallel, right? And parallel lines indicate a main effect, okay? But when the lines aren't parallel, then we're going to end up with a spreading interaction or an ordinal interaction. And effectively, what the interaction is showing us is that there's a significant difference within this condition between the two levels of this independent variable, and it's not significant here. We talk about this statistically as the slope of this line. Sorry to bring math into this, but the slope of this line from here to here is significantly different from the slope of this line. Okay. Now, there are other forms of interactions besides ordinal interactions. So now we're just going to go out on a limb here. Like, what if caffeine had a positive effect when you didn't sleep, but actually had a negative effect when you got 8 full hours? So maybe when you didn't get enough sleep, caffeine sort of balances you out and helps you do well on the test. But when you get a full night's sleep and you have caffeine, you're really jittery and it makes you hard to concentrate, so it actually makes your performance worse. So this would look something like this. So when they got 4 hours of sleep and no caffeine, they did poorly. When they got 4 hours of sleep and some caffeine, they did better. But when they got 8 hours of sleep and no caffeine, they did really well. But when they got the caffeine for that hour of sleep, they actually did worse. When we convert this to a line graph, this looks like an X. This is a crossover interaction or a disordinal interaction. And in this pattern, what's happening is that the pattern of the independent variable actually changes when we include that second independent variable into the model, right? The effect of caffeine on intelligence is the opposite. It's completely different depending on how much hours of sleep you got, okay? So we talk about this as a crossover interaction. The trick to the crossover interaction is that you've got this sort of X-looking pattern. And again, it's not just that the slope of this line is significantly different from the slope of this line. It's that the sign of that slope has completely changed. This slope is a positive slope because it's increasing. This slope is a negative slope because it's decreasing. When we do our analyses for these, and again, once you end up, what you may end up in grad level stats where you'll be talking about doing the analysis for this. We talk about this as sort of simple slopes analysis. We would also be asking the question, are these means different from each other? So that is Factorial Designs. As always, if you have any questions, you can feel free to shoot me an email.